Today we're going to be talking about the graphs of different polar equations. So polar opens up a lot of things that we can't necessarily do in rectangular equations or function equations. So the first one we're going to graph is r equals 3 sine theta. We will initially do this by simply plugging in values, and to speed this up, so we're going to plug in 0, plug in 3, and so on. I'm going to let the calculator help us with this. So on the calculator, we want to make sure that we are in degree mode since we're plugging in degrees. Then I'm going to go to my y equals, and I'm going to do 3 sine x. Okay, what I'm going to use is the table feature to quickly plug in all of these values. So I'm going to go to second table set, which is over the window button. I want to start at 0, and I want my delta to be 30. That's going to be our steps. Then if I go to above graph, it says table, second table, all of those values are there. So I'm going to copy those values down into the chart and round to the nearest tenth. So these are our values. So I'm going to go to each of my degree measurements and go out the certain distance. So at 0, we're at 0. At 30 degrees, which is going to be the second line, we're at 1.5, so there's 1, so 1.5 is going to be there. 60 degrees is this one, so we're at 2.6, so it's a little bit more than halfway. At 90 degrees, we're up at 3. At 120, we're at 2.6. At 150, we're at 1.5. And then 180 is at 0. 210, which would be this line right here, is at negative 1.5. So remember, if we've got a negative r, rather than marking it on this side, I'd mark it on the opposite side, which is already marked, and it's just going to repeat those points. Okay, so for example, 270, negative 3 is that point here. So when I connect my dots, we get a circle. So I encourage you to pause this and try this one. Again, we're going to let the table feature be used to generate the points. So we've got 2 minus 2 cosine x. We go to the table and transfer those to our chart. And then we will graph. So 0 is at 0 again. 30 degrees at 0.3. 60 is at 1. That's that dot. 90 is at 2, so 1, 2. 120 is at 3. 1, 2, 3. 150 is at 3.7. That one. And 180 is at 4. Then we start going back down. So 210 is at 3, 1, 2, 3.7. 240 is 1, 2, 3, 2, 1. 0.3 on 330. Okay, so this one, we start at the origin, we go out a little bit, around, and back in. Okay, this next one, we're going to change our delta to 15. So we have 5 cosine 3x. When I go to my table set now, I want to start at 0 and go up by 15s this time. Okay, and we'll take those and again transfer it to our chart. All right, so 5, 3.50, negative 3, negative 5, negative, and so on. So it goes up and down, which should not be surprising since it's a trig function. Then we're going to graph. So 0 is out 5. 1, 2, 3, 4, 5. The next one is 15, so we're going to be out 1, 2, 3.5. Then we're at 0. 45 degrees, which is this one right here, we're plotting negative 3.5. Okay, at 60, which is here, we're at negative 5. And then the next one's negative 3.5 and 0 again. At 105, which would be this one here, we're at 1, 2, 3.5. 120 is at 5. to 3.5 and 0. And then at 165, we're at a negative 3.5. 180 is at negative 5, and then we're going to start repeating these dots again. So this graph, when we connect the dots, we get a flower-looking thing, and in fact, this is called a rose. So we graphed some nice, pretty graphs, and what you should have noticed is they were very symmetrical graphs. So we want to look at the impact of if the equation has a sign in it versus a cosine. So I have 3 graphs here. The 2 that have cosine are both symmetric to the x-axis. The one with sine is symmetric to the y-axis, and that will always be true. So if it has a sign, it's symmetric to the y-axis, also known in polar, since there really isn't x and y's, would be theta equals pi over 2. Cosine is going to be symmetric to the x-axis, also known as the polar axis. Okay, this is easy to remember because sine goes with y, cosine goes with x, just like it has for everything. Right, so let's look at these different types of graphs. So in polar, we have these special, what we call classical curves. So I already mentioned the name of this one, a rose. The general formula for a rose is going to be a cosine n theta or a r equals a sine n theta. And here's a couple of examples of what those might look like. And we've already drawn one of those. Next is a lemniscate. And we haven't done one of those. But if you take it r squared equals a squared cosine 2 theta, same with sine, you get kind of an infinity looking graph. A limacon is going to be a plus b cosine theta or a plus b sine theta. And you can get a little curve like this, a little curly. Sometimes they'll go on the outside. Okay. A cardioid looks very similar formulaically, but notice that rather than a plus b, it's a plus a. So if the two a's are the same, those two are the same, we get a cardioid. And we did graph one of those. The second graph we did was a cardioid. So 2 minus 2 cosine theta, and this is the graph we got. Okay, a circle. Obviously, if you've got r equals a, so r equals 2 is going to be a circle like that one. But they can also come in the form of a cosine theta or a sine theta. And they will look like this depending on if it's a sine or a cosine. For example, the first graph we did was 3 sine theta. So we had a circle symmetric to the y-axis with a radius or a diameter of 3. And last is just a line, so just our theta equals something, theta equals pi over 6, and we draw that line. Okay, so I encourage you to pause and try to fill in these names. R equals 4 is a circle. If you go around 4, theta equals 30 will be a line. R equals 3 sine theta will also be a circle, symmetric to the y-axis. 5 cosine theta will be a circle, symmetric to the x-axis. This one here is a lemniscate. Okay, this is a rose. This one is a rose. And last here we have a cardioid, because those two values are the same. Okay, now I'm going to show you how we can do these graphs on a graphing calculator. So I've got r squared equals 4 sine 2 theta. So first we'll identify the type of graph, which is a lemniscate. On our calculator, we're going to go to mode. We're going to stay with degree mode because that's easier. Now if we go to function, last unit we talked about parametric. Now we're going all the way over here to polar mode. Okay, then we're going to go to y equals. And now, rather than y equals, it says r equals. So I want to do r equals, so r squared equals 4 sine 2 theta. So in order to solve for r, I'm going to do the square root, and then 4 sine 2 theta. Now technically we'd need to do both the positive or the negative, but it'll end up repeating these points. Okay. Now if I go to my window, for my thetas, you need to go from 0 to 360 since we're in degrees. Theta step, maybe I'll go by ones is fine. The smaller that is, the more accurate your graph will be. And then I'm just going to graph it on a standard window. So we hit graph. And there is my lemniscate. This is kind of a squashed graph. So what I'm going to do is do a zoom square. We'll make it so the aspect ratio matches. So it will actually look like what it's supposed to look like. Okay, so I zoomed it in a little bit. For my graph, I'm going to go, you can trace points if you want to. So trace to 30. You can trace and hit like 30, or you can go back to the table and get your values from here. So I'm going to copy this down onto my graph. So I found some of the points, like 45 is at 2, and on either side is 1.8, drew my loop. Same thing over here, draw my loop. Okay, this next one is a limacon. We'll go ahead and do this in the calculator again. See what this graph looks like. So this one's got our nice little loop on the inside. Okay, I'll go back to the table and we'll get those table of values and plot this shape. So there are those points. Again, plotting the main ones you can do every 15 or every 30. And get a nice pretty graph. Okay, now that we have gotten an introduction to these classical curves, next we're going to graph some of these, not all of these, without a calculator. So first, knowing what each equation goes to which graph, then we're going to plug in easy values like 0, pi over 2, pi, 3 pi over 2, and knowing the symmetry, if it's a sine or a cosine. So we're going to start with circles. Circles in the form r equals a cosine theta, r equals a sine theta. We know what a circle looks like. This one, cosine, is going to be symmetric to the x-axis. We know that. And I'm going to plug in zero, pi over 2, pi, and 3 pi over 2. Or you could use degrees if you feel like it. Okay, so here, cosine of 0 is 1, so 1 times 3 is 3. Cosine of pi over 2 is 0 up at the top of the circle, so this is 0. Pi is negative 1, so this would be negative 3. 3 pi over 2 is 0. Okay, so at 0 degrees, we're at 1, 2, 3. At pi over 2, we're at 0. At pi, we're at negative 3, which ends up back at this point. So we have these 2 points, which isn't, super helpful, but we know this is a circle, and we know that it's symmetric to the x-axis. So we'll just fill in the rest as a circle. Okay, so I encourage you to pause it and try r equals negative 4 sine theta. So again, we'll make a table of values. Sine of 0 is 0. Sine of pi over 2 is 1, so this will be a negative 4. Pi will be 0, and 3 pi over 2 will be a positive 4. So again, so pi over 2 is going to be down here at negative 4. 0 is at 0, 3 pi over 2. So we get these 2 points again. Great. But we'll come in here because we know it's a circle and we know it's symmetric to the y-axis. So that's how we can graph circles without the use of a calculator. Next up are the cardioids. So I'm going to refer back to the first one that we did. Okay, and I'm just now noticing we're going to be graphing the same one, but that's okay. A cardioid, if you think of the word cardio, you think of heart. So this is a heart-shaped graph. That's what all cardioids are going to look like. Okay, so the first thing that you're going to identify is this is a cardioid because it's 3 plus 3. The sine theta means it's going to be symmetric to the y-axis, and then I'm going to plug in my 4 points. So 0, pi over 2, pi, and 3 pi over 2. Sine of 0 is 0. So 3 times 0 is 0, plus 3 gives me 3. Sine of pi over 2 is 1. So this is going to be 3 plus 3, which gives me 6. Sine of pi is 0. So we get 3. And 3 pi over 2 is negative 1. So we get 0. So at 0, we're at 1, 2, 3. Pi over 2, we're at 1, 2, 3, 4, 5, 6. And pi, we're at 1, 2, 3. And at 3 pi over 2, we're at 0. Okay, again, that's not a whole lot of information, but we know it's going to be a cardioid. So this is where the heart shape of it's going to be. And then it's just going to loop around to fill in the rest of that. Okay, I want you to try to do this one by hand, and yes, we've already done it, but try this one. So we'll plug in 0, pi over 2, pi, 3 pi over 2. Cosine of 0 is 1, so we get 2 minus 2, which is 0. Cosine of pi over 2 is 0, so 2 minus 0 is 2. Cosine of pi is negative 1, so this will be a 4. Cosine of 3 pi over 2 is 0, so we get another 2 there. So 0 is at 0, pi over 2 is at 2. 1, 2, 3, 4, and 2. Get that part, and loop it around. Okay, so it doesn't have to be super accurate, but what I'm looking for are the 4 main points and then the general shape. Okay, let R be the region inside the graph of R equals 3 and outside of the graph of R equals 3 and inside the graph of 3 plus 3 cosine. So R equals 3, 1, 2, 3 is just a circle at 3. For this one, we'll go ahead and plug in our values. But you're probably already seeing some patterns. We know this is going to be symmetric to the x-axis. Cosine of 0 is 1, so we get 6 here. Cosine of pi over 2 is 0, so we get 3. Cosine of pi is negative 1. Okay, so we plot these points. So 0 is out here at 6. Then we're at 3, 0, 3. So the cardioid looks something like that. And we want the area outside of the circle, but inside the cardioid. So we're looking for something like this. Now, if you take calculus, you will learn how to find the area of something like that. Finally, we're going to look at the roses. Okay, so roses are in the form a cosine n theta or r equals a sine n theta. First, we're going to look at the relationship between the equation and different types of roses. So we're going to graph these equations. So 3 cosine 2 theta. When we graph this, we get this nice pretty looking rose, which has 4 petals. Now I'm going to change that number to a 3. And graph. And we get 3 petals. So we need more information. I'm going to change this to 4. And graph. And we have 8 petals. All right, well, what about 5? There are 5. Now at this point, you can pause the video and play around with different numbers, but hopefully you sort of see a pattern here. Okay, when our number here, 2, 4, was even, we ended up with 2 gave us 4, 4 gave us 8. When it was odd, 3 and 5, 3 gave us 3, and 5 gave us 5. So our conclusion is when n is even, there are 2n petals. When n is odd, there will be n petals. Now plugging in just the quadrantals is not going to give us a good enough idea with these ones. Okay, so what we're going to do is use the rectangular graph and the fact that we know how many petals and the symmetry. So now we have 3 sine 2 theta. So we know there's going to be 4 petals, and we know they will be 3 units long, and we know that it is symmetric at a minimum to the y-axis. So I'm going to graph this like we did before Christmas using the rectangular graph. The amplitude is going to be 3. The period is going to be 2 pi over this number here. So 2 pi divided by 2 gives me a period of pi. So I'm going to have a 3 here, negative 3 here. I'm going to take pi, and I'm going to leave some space because we need 4 petals. And then divide that by 4. So pi over 2, pi over 4. This is pi over 4, 2 pi over 4, 3 pi over 4. And then I'm going to graph sine. Sine starts at the midline and goes up. Okay, these maximums and minimums are going to be the location of the petals. So you could graph these two and then use the symmetry, or you can just continue on our graph. So this will be 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. Okay, so each of those max and mins are the location of the petals. So our first one is at pi over 4. So I'm going to go to pi over 4. I'm going to go out 3 units. 1, 2, 3, 4. The second one's at 3 pi over 4, but it's at negative 3. Okay, so we could use these two. Oh, not too far on that one. We could use these two in the fact that it's symmetric to the y-axis and reflect. That means there has to be one here and there has to be one here. Or we could continue the graph and we've got the 5 pi over 4 and the 7 is at negative. And then we draw our loops. Okay, again, I encourage you to pause it and try the next one. So this one's going to have 3 petals. It's going to be symmetric to the x-axis. The amplitude is 4, and the period is 2 pi over 3. So 2 pi over 3 makes this pi over 3. makes this pi over 6, half of that. So 1 pi over 6, 2 pi over 6, 3 pi over 6. And if we need to extend our graph, we will. This one is a cosine, so it's going to start at the maximum, then go to the midline, to the minimum. And we could continue the graph, but from this, we have our locations. Okay, the location of the first petal is going to be at 0 degrees out 4. 1, 2, 3, 4. The second one's going to be at pi over 3, which would be up here, but at negative 4. And last one's going to be at 2 pi over 3 at positive 4. Now they should all be symmetric. If you end up with like 2 of them in the same quadrant and nothing on this half, that's not correct. And then we'll graph our rows. So that's how we can graph these polar equations without the use of a calculator.